Welcome, everyone. I'm Sergio Casas. I'm the tech lead manager of our perception and behavior reasoning team here at Wabi. So Wabi, for those of you that don't know, it's a 3-year-old company focused on self-driving trucks. And yeah, we've prepared this tutorial with a lot of effort. It's a full-day tutorial. It's very comprehensive beyond autonomy as it's typically perceived by computer vision people, like kind of just from sensor to the plan, but there's a lot more to self-driving that we will be covering today. So last year, we did it in Vancouver as well. And we thought it was a huge success based on the positive feedback from people. So I'd like to do a very quick show of hands. Can you raise your hand if you were there last year and you are a repeat, basically? Okay, awesome. Almost no one then, which is great. I think this tutorial is anyway meant for kind of everyone, whether you are an expert in self-driving in some specific area and you want to learn more about other areas, or maybe just getting started and just want to know more about the field. This is great for you. Hopefully, if you are on the second bucket, this will motivate you to do like a PhD on self-driving or maybe join a company like ours. So I actually think it's a great timing to join self-driving, like the efforts towards self-driving based on where we are with AI today and the rapid progress in the last couple of years. And today, I actually have some great news to announce. I'm sure Raquel Hurtasun, our CEO, would love to announce them herself, and she loves this conference. She would really like to be here, but you can understand she's been really, really busy raising this Series B that we just announced this morning. So this is huge for us. It will enable us to do driverless trucks next year. And you have the link there if you're curious to read more. And there's also this other blog post written by Raquel herself that was also released today. You have the QR code there. I'll leave it a couple seconds in case you're interested, but it talks a bit more about the vision of the company and kind of the next steps of that company. There's a very long 15 minutes video that I won't be playing, of course, in this intro, but it's very cool. So go watch it later. I'll play now this video. This is now about a year old, but I think it still summarizes pretty well what we do at Wabi and in a short amount of time.
The future of trucking is autonomous. That means safer roads, a stronger supply chain, a new era of logistics. At Wabi, we believe that to unlock this new era, we need to build the next generation of technology. Meet the Wabi Driver. Powered by our AI-first approach, the Wabi Driver is ready for trucking now. Let's take a closer look. The Wabi Driver has two components: the advanced virtual driver as software, together with sensors and compute as hardware. It includes LiDARs, cameras, and radars for increased redundancy and safety. At its core, the Wabi Driver is a full autonomy stack. From sensing the world to decision-making, the entire system as a whole automatically learns from data. Thanks to Wabi World, our groundbreaking simulator, we're able to expose the Wabi Driver to the vast diversity of experiences needed to hone its driving skills, which would be impossible otherwise. This makes it safer and smarter before the wheels even start turning. The Wabi Driver is a single AI system that is both modular and interpretable, which means we can trace every choice it makes, and we can validate its decisions. The Wabi Driver has superior generalization capabilities. It can apply learned skills to new situations and geographies it has never seen before, unlocking new autonomous routes with unprecedented speed. We built the Wabi Driver with production intent from day one. It's designed to be easily integrated on the assembly line for a safe, reliable, and scalable product. And it's highly flexible, adaptable to multiple redundant truck platforms and sensor configurations. We are unveiling a new paradigm, safe, scalable, and ready for the road. The future of trucking is autonomous. The future of trucking is here.
Hopefully you could hear another room. But yeah, since then, this was this video was has more than 1 year now. Since then, we've actually been driving on public roads in autonomy for last year in Texas, actually. And we've also been regularly delivering loads for our customers, including some of the largest shippers in North America. So now we'll go a bit more into kind of autonomy for a bit. I'll talk a bit about Wabi's approach, and one of our latest, I'll do a quick, I guess, reveal of one of the papers we have at CVPR, and then we'll move on to the tutorial topics. And the tutorial is more an unbiased view of the field rather than our work. We just basically introducing our company in this introduction. So autonomy stack, we have sensors at the very beginning. We use basically different sensors like camera, LiDAR, radar, which is really great to have redundancy, and they have their pros and cons, as we'll see in later parts of the presentation. It's also a good thing that for tracking, the economics work a lot better, so you can put a very high quality sensors on that track compared to, like, let's say, passenger vehicle. We also believe high definition maps still have a lot of value, and even though they cannot be trusted 100% of the time, and you need to understand when the map has changed, it's still a very strong prior for the different tasks in the stack. By the way, this overview, I want you to think more about these modules at a kind of more high-level capabilities rather than actual modules that are cascading. We'll get later more into the different paradigms for autonomy, but here I'm talking more at a high level what a basically self-driving vehicle needs to reason about. So it needs to do perception to some degree, and typically that's done with detections and tracks, meaning that we are trying to essentially see where the other agents are in the road, kind of maybe their kinematic state a bit, the history, so that then later on we can actually understand what they might do in the future. This is very important because we actually don't know for certain what other agents are going to do. So we need to be very smart about how we understand our uncertainty about the world and how we can then plan a safe maneuver around these vehicles. And finally, that maneuver or that trajectory that we plan needs to also be executable by a controller, and basically the vehicle being able to follow the actuary commands. So you might be thinking, we've been doing research as a community in self-driving for about 2 decades now, and self-driving are not still widely deployed out there. Why is that? So self-driving is actually a very hard problem because most of the time it's very easy, and that has been solved already. And many companies have products that can drive most of the time in supervised autonomy, where there's a driver kind of without that safety driver without touching the wheel. And most of the times the system is driving autonomously. But there are certain cases that are very hard. Here you have some images. There are some animals like elephants and a bear there. The second image is actually very dear to our hearts. The very, very first time we engaged in autonomy in Texas, we saw that vehicle with the house. And of course, you can imagine, like, we were watching it, and it was a pretty tense moment the first time you put it out there. The system reacted very well around it, even though probably it hadn't seen something like this before, although it had seen many, many things in simulation. And the third picture is of a chrome car that we saw in Toronto. And yeah, for a camera, this is kind of one motivation to have redundancy in sensors. For camera, maybe not so hard for this vehicle, but you can imagine if the trailer of a big truck was painted the same way and it reflected basically everything, doing perception can be pretty hard with camera only, which you don't get like the depth aspect, like the geometry. So that's a great motivation for LiDAR and radar. And it's not just driving that it's hard around these examples. It's also the fact that these examples exist and we need to account for them means that we need to test very, very thoroughly, especially in simulation, where we can recreate these ones and create new ones too, like purely synthetic ones. So now we'll talk a bit about the modular autonomy. So this is the industry's traditional approach, but it has kind of hit a wall. So in the traditional approach, before I ask you to kind of think of these modules as capabilities and kind of general ideas of what the self-driving needs to reason about, self-driving vehicle, but here it's actually taken very literally. And in this diagram, they are meant as different modules, basically cascading modules. And what this means is that there are very narrow interfaces between these different modules. And essentially, there's a huge team typically dedicated to each of those modules, or maybe parts of the module actually. And these teams are fairly siloed. They have their own metrics typically that they are trying to drive up, but those metrics are maybe not quite what we care about. Like they don't correlate that well with driving in the real world. And so you have these massive amounts of people working on different teams, trying to optimize things that are not quite what we want. And the fact that it's modular and it has these components and these very thin interfaces also means that if there's any mistake, let's say a perception mistake, then prediction will do even worse because it has very limited information about the world compared to what perception had, which saw the sensor data. At least it knew that it didn't know about it. Now prediction is trying to make sense of some perception output that doesn't make a lot of sense. And actually, so that's one way, kind of from upstream to downstream, but it can happen the other way too. Like let's say the planning team now decides to change something on the planner. And now the prediction team also needs to adapt because the planner now assumes a certain properties of that input. So they need to go and change what they did as well. So basically a change or mistakes in any parts of the pipeline cascade both ways. And yeah, this can be really, really hard to develop, to basically have a agile development here. And of course, because it has huge number of employees, it's also very expensive. Some of the companies with this paradigm burn billions of dollars every year. So kind of the other paradigm that has emerged, which is a complete opposite, is this basically end-to-end neural network, where we have a neural network that consumes the maps and sensors and outputs directly the decision. And it's actually very difficult to make progress with this approach because of several reasons. First, let's say the system doesn't do something well. Really, the only way you can go fix it is by either designing this neural network again or adding examples to your training data. But it's all very indirect and it's very hard to get basically kind of a quick development cycle where you get a lot of feedback back from testing. The fact that it's not interpretable, it's also a problem. First, it's a problem because it's hard to understand for developers what the system's doing. But second, it's also a problem for regulators, which expect some level of reasoning in that vehicle that can explain why it did a certain action. And finally, it also requires a huge number of examples for training. Training can be very long and very costly too. So we are kind of shifting the cost from a huge number of employees in the previous paradigm to a huge amount of dollars for training this system end-to-end. And the reason is that end-to-end training can be inefficient because, or at least if it's solely end-to-end training, it's hard to learn about everything that's happening on the world just from your kind of an expert controller or let's say driving in simulation, but with only feedback from the right action and not from any kind of world understanding. And finally, since everything needs to be tested, or we should test everything before going to the road and be confident before actually going driverless, this can be very hard to test because it basically grows exponentially the amount of tests that you need to do with the amount of factors that could change the output of your autonomy. So in this case, since it's end-to-end, anything that changes in the input can change the output. And we cannot really test, let's say, for example, our perception doesn't do very well with a certain type of clothes and maybe a hat, when they are wearing a hat and carrying some object. We would know this, let's say in the modular approach, we would know this because we will have metrics at the perception level and we can bucketize it by different types of actors. And then we can know this well in advance. Let's say if we've only seen a person on the side of the, on the sidewalk with those properties, and we didn't do very well. But in this type of system, you will only realize you don't do very well when you actually encounter that person in a situation that you should react, right? Because basically the only feedback you are getting is from the driving itself, not from your understanding of the word. So that's quite limiting. So this is the paradigm we are proposing instead. You get maps and sensors. You are able to learn both from unsupervised data through this foundation model with generative AI, and you are also able to learn with supervised fine-tuning this additional layer of reasoning that can output interpretable representations. So coming back to what I was just saying, this upper layer of reasoning can be supervised and can also be interpreted. So it can be well understood what the model is reasoning about, and this can be great for both training, which we can encode a lot more of our knowledge, as well as testing by getting to know early what the system as a whole cannot do by understanding what the system doesn't understand of the word. And this also unsupervised pre-training with supervised fine-tuning is a very powerful framework because it allows you to leverage the scale of your collected data, which is cheap on the foundation model side. And it also allows you to essentially inject your knowledge through supervised tasks that we'll talk a bit about later in the other sessions. So it's still AI first. The system is end-to-end trainable. It's interpretable, which can help with verification and safety. It's scalable because it does this complex reasoning. We can tell from similar situations whether it's going to transfer to another one or not, better than in the end-to-end paradigm. And finally, it's very capital efficient. We don't need a huge team. You can think of the backbone of the reasoning happening in the foundation model, which basically has the pros of the end-to-end paradigm. And then we also don't need thousands or hundreds of thousands of essentially annotated cases with a lot of human knowledge, because we only need to fine-tune this model for the reasoning that we want. And here's a teaser, maybe a glimpse into what I mean here. This is a paper that it's here at CVPR. We call this our occupancy foundation model. Maybe contrary to other foundation models, it doesn't try to output the sensor data itself, like trying to reason about basically the future sensor data, which it can be hard to use. It's not clear how to use a word model where you're predicting images or LiDAR. Instead, what we are doing here, which is the outputs that you see on the left, we are trying to reconstruct the geometry of the word, like everything that is going on in the world around us as occupancy. So actually, that's a 4-dimensional occupancy, X, Y, Z, and time, that we can actually query in the motion planner, right, and understand which parts are occupied and which not. So it's interpretable. It can understand what that couch in the middle of the highway is, which we actually found some time ago in Texas. So this is the sort of thing I'm talking about, where we are bridging the gap between kind of some end-to-end black box and interpretable representations. Sorry. Yeah, so if you're interested, that's the project website. You can learn a bit more about it. I'll talk a bit about it in a later session that we have. And that the oral presentation is tomorrow, Thursday at 1 p.m. and the poster also Thursday at 5 p.m. Cool. Now we move a bit from autonomy to simulation, and we've really flipped this pyramid. So typically or traditionally, there's essentially a little bit of simulation that developers do to understand the performance of the system. Then there is more closed course testing. And finally, there is a lot of testing in the real world. And this is kind of, okay, like it's been working to get it to work to that level that we were talking before, where it can do well on most of the cases. The problem is, first of all, you don't get to see a lot of interesting cases in the real world. If you're driving on the highway in Texas, most of the time, nothing really is going on until it does. And the second thing is that you get a lot of exposure basically by running all these millions of miles or even billions of miles in the real world, which can be dangerous unless you have a really, really good safety case. So instead, the approach that we've taken at Wabi is to do a lot more simulation. That's basically at the core of what we do. We actually developed the simulator before we had even collected real data, or starting developing the simulator before we even had started collecting with our trucks. Then you do closed course testing, of course, which is great to see the transfer from sim to real. And then once you are confident that your analysis and simulation basically can transfer to the real world, you go and just to verify that everything is working as expected, you do some testing in the real world, but by no means the amount that is typically done. And this is just kind of a quick overview of Wabi World, which is our simulator. Essentially, the philosophy behind it is that the world is out there. So if we can clone it, we can get the realism, but also the diversity of the world. And that's what we are trying to do here. We are trying to build this digital twin where we can simulate the different sensors. We can reconstruct objects that then we can place in the scene in very modular and controllable ways. We can generate complex scenarios for testing, but also for learning how to drive. Essentially, you can put your autonomy now and see how it would do in closed loop and learn from that feedback. Cool. So now that's it for kind of talking about Wabi as a company and kind of our vision and what we do. And this is the schedule for today's tutorial. So I'm doing the intro. Andre will be talking about hardware and sensors. I'll have another session on perception and motion forecasting. And then Kelvin will talk about motion planning and control. We'll have the lunch break. Andre will talk again on intelligent data mining, which is basically all the data that fits this system. We'll talk a short session on vehicle-to-vehicle communication, which will be very, very relevant in a few years when basically autonomous vehicles are deployed at scale. We'll talk about that simulator that I was talking about, as well as the behavior models that are inside with Siva and Kelvin. And finally, after an afternoon break, Andre will wrap it up with the mapping and localization sessions. Cool. So this is just a very, very, very high-level overview of what you'll see. On hardware and sensor session, we'll cover sensing, like the different sensors that are on the truck, what's their purpose, kind of what's the latest today, as well as the same for compute. We'll then go and talk about perception. So how can we utilize all these sources of information efficiently to perceive 3D object, but not just a few categories of interest like vehicle, pedestrians, and bicyclists, but actually in an open world where we can find couches on the highway like we saw. We'll then talk about motion forecasting, which is also called prediction in the industry. So this is, how can we anticipate how the world might unroll in all the possible ways that it might. And then the later part of the stack, how can we reason about all these interpretable representations and put them into an actual plan, a decision that we can execute. And then we'll switch more to the offline world. We'll talk about intelligent data mining. So specifically from all these kind of process from the moment you collect data to the moment you evaluate the networks, will focus on data curation and labeling. So basically how we select the best data before it's labeled and how do we label it. We'll talk about vehicle-to-vehicle communication. So how can we communicate in a smart way between different agents, autonomous agents. I talked about this digital twin of the world, and we'll get into a lot more details later in this session, and including how can we simulate our self-driving platform as well, not just the world itself, but the ego vehicle. And part of this simulation is also the behavior of the other agents around us. So we'll talk about this behavior modeling in detail. How do we represent a scenario on one hand, and also how do we design these intelligent agents that can navigate the virtual world. And in the afternoon, after the afternoon break, we'll talk about mapping. So what's the end-to-end pipeline basically to create these beautiful high-definition maps that gives us a lot of prior knowledge, as well as how can we know where the vehicle is located in the world to centimeter level accuracy. This is my last slide for the intro. I think we'll have questions basically at the end of every session, if there's time according to the schedule. And otherwise, there will be also extended QA during the breaks, as well as at the end of the day. And yeah, I mean, we are hosting, you can ask, I think, definitely in person and in Zoom as well, right? Yeah. Cool. Thanks, everyone. That's it for the intro.